Hello. In continuation with the laws of chemical combination, we have this third law in the series, law of multiple proportions. This is about interaction between or combination between two elements which give rise to two or more compounds. Two elements combine to produce two or more compounds. Generally, we commit a error here when we suppose it is two or more elements form two or more compounds. No. Same two elements which combine and give rise to two or more compounds. Hydrogen and oxygen combine to give rise to hydrogen and oxygen combine and give rise to water and hydrogen peroxide. Carbon and oxygen combine to give rise to carbon monoxide and carbon dioxide. Two elements giving rise to two compounds each. We have nitrogen and oxygen which combine and give rise to more than two compounds. It is nitrous oxide, nitric oxide, nitrogen trioxide, nitrogen tetroxide, nitrogen pentoxide. In these five oxides, four of these have two nitrogen atoms, one has one nitrogen atom. We may rationalize for discussion of this law only and write it as N2O2 because it will not change the ratio between weights of nitrogen and oxygen. We have this is nitrous oxide, also called laughing gas. This is nitric oxide. This is nitrogen trioxide, nitrogen tetroxide, nitrogen pentoxide. I write here in the end nitrogen pentoxide. Here, weight of nitrogen, in this case 14 into 2 it is 28, 14 into 2 it is 28, 14 into 2 it is 28, it is 28 and here also it is 28. Oxygen it is 16, 16 into 2 it is 32, it is 48, 64 and 80. What I want to convey is weights of nitrogen are same in all the five. Weights of oxygen are different. In this, weight of hydrogen is 1:2, 1:2. Weights of oxygen are different, 16 here and 32 here. Weights of carbon are same, 12 here, 12 here. Weights of oxygen are different, 16 here and 32 here. This gives us an idea about defining the law of multiple proportions. Defining the law of multiple proportion, it says when different weights of an element, different weights of an element combined with same weight of the other element. These weights, which are different weights, are in a simple, means small, whole number ratio. I repeat, when different weights of an element combined with same weight of the other element, these weights are in a simple whole number ratio. When different weights of oxygen 16 and 32 combined with same weight of hydrogen, these are in a simple whole number ratio. Different weights of oxygen 16 and 32 combined with the same weight of carbon, the weights of oxygen, the weights which are variable, are in a simple whole number ratio. This is the law of multiple proportions. Two elements, not two and more elements, two elements combine to form two, at least two or more number of compounds. Weights of one element, the different weights of one element, which combined with same weight of the other element, are in a simple whole number ratio. 16, 32, 48, 64, 80, these are in the ratio. Divide by 60. 1 is to 2 is to 3 is to 4 is to 5. This is the law of multiple proportion. Law of definite proportion was about number of elements present in a given compound. It was about weights of elements forming a given compound which may have been prepared from different sources. This is about two elements, nitrogen and oxygen, which combine to form two or more compounds. Then weights of variable weights of one element, which combine with the same weight of the other element, must be in a simple means small, whole number ratio. This is the law of multiple proportions. After this discussion, illustrations with three different sets: hydrogen and oxygen, carbon and oxygen, nitrogen and oxygen. We shall attempt to define this law and then attempt some numerical problem for it and attempt some numerical problem from it. Let us define this law. Let us define this law. Then two elements, say A and B, combine and give rise to two or more compounds, then weights plural of one element which combine with same weight of the other are in a simple whole number ratio, are in a simple whole number ratio. This is the law of multiple proportions. I think it must be clear. Here we are using singular fixed weight. Here we are using plural weights. Weights of one element. These weights are variable as we found in case of oxygen in oxides of nitrogen. 16, 32, 48, 64, 80. Weights of one element is combined with same or fixed weight. This is singular and this is plural. Of the other are in a simple whole number ratio. This is the law of multiplication. Let's have a question, a numerical problem. 11 grams of an oxide of nitrogen equals 5.6 liters of 5.6 liters of nitrogen, 15 grams of another oxide of nitrogen equals same volume of oxygen. Show that it illustrates the law of multiple proportions. This is the question we shall be attempting after discussing examples and then definition of the law of multiple proportions. Now, there are two oxides, an oxide, another oxide. This oxide of nitrogen evolved this volume of nitrogen at STP, so that we can apply Avogadro's law. 15 grams of another evolves same volume of oxygen again at STP. We have done in mole concept. 1 mole of nitrogen, which has weight equal to 14 into 28 grams, occupies a volume of 22.4 liters. 1 mole of oxygen, which weighs 16 into 2, 32 grams, occupies a volume of 22.4 liters at STP. From this relation, we shall determine the weight of this nitrogen. Subtract from 11, it will give us a weight of oxygen. Calculate weight of oxygen by this method. Subtract it from 15, it will give weight of oxygen. From these two sets of values, we shall try to illustrate the law of multiplication. Let us attempt it like this. Let us attempt it like this. This is the first oxide and this is the second oxide. Weight of oxide of nitrogen, it is 11 grams. Weight of oxide of nitrogen is 15 grams. It has evolved volume of nitrogen at STP 5.6 liters, volume of O2 at STP It is again 5.6 liters. We know, and definitely we know it from mole concept. We know my previous lectures on mole concept when we related moles with this volume. It was called gram molecular volume. We know 22.4 liters of nitrogen at STP, its weight is 14 into 2, 28 grams. 5.6 liters will have 28 into 5.6 over 22.4, it is 7 grams. So this oxide of nitrogen has 7 grams of nitrogen. Therefore, weight of oxygen is equal to 11 minus 7, that is 4 grams. We know definitely 22.4 liters of oxygen and STP is equal to 16 into 2, 32 grams. 5.6 liters, 32 into 5.6 over 22.4, and this is 8 grams. Weight of oxygen is equal to 8 grams. Therefore, weight of nitrogen is equal to 15 minus 8 is equal to 7 grams. What is common in these? Weight of nitrogen 7, weight of nitrogen 7. What is different? Weight of oxygen 4 grams, weight of oxygen 8 grams. Weights of oxygen 4 and 8, which combined with same weight of nitrogen, are in the ratio 4 is to 8 or 1 is to 2. This is the law of multiple proportion. Weights of oxygen which have combined with 7 grams, which is a fixed mass of nitrogen, are in the ratio 4 is to 8, 1 is to 2. This is simple whole number ratio, and definitely it illustrates the law of multiple proportions. It illustrates the law of multiple proportions. Nitrogen and oxygen we have done form 5 oxides. We have selected 2. I don't know which are these. A known rate of the first oxide evolves this volume of nitrogen. A known rate of the second evolves this volume of oxygen. By simple calculations using unitary method, we shall apply the method in full. This is our initial stage, preliminary stage. No guesswork, no shortcuts. Success does not have shortcuts. You need to know everything in details. No shortcut. You will not skip any step, not skip any word, and move on systematically. A stage will come when we shall be applying the shortcut methods, but not now, not at this stage. This will be counterproductive. I have another example, another numerical problem. This is about compounds involving hydrogen and oxygen, hydrogen and oxygen form two compounds. We have done the compounds were water and hydrogen peroxide. A compound had, still has 11.11% hydrogen. The other has the other has 5.93% of hydrogen. Show that these values illustrate the law of multiple proportions. It illustrates the law of multiple proportions. We shall bifurcate this space. First oxide, we have second oxide. First oxide, hydrogen is 11.11%, hydrogen is 5.93%. Therefore, oxygen is equal to 100 minus 11.11, 88.89. Oxygen 100 minus 5.93, 94.07. Keeping a similarity, these weights, let us divide by weight of hydrogen in both cases to make up the whole numbers. The hydrogen oxygen ratio is, let us go a step back, 11.11 is to 88.89. Hydrogen oxygen ratio is 5.93 and 94.07. To make these whole numbers, we shall divide these two by the smaller one. It is more convenient. We are dividing these two with the rate of hydrogen, and here also we shall be dividing by the rate of hydrogen. Either both expressions are to be divided by rate of hydrogen or by rate of oxygen. Not like this, hydrogen here and oxygen here, it will give us a confused result. Rather, it will be no result. Divide both these by 11.11 rate of hydrogen, divide these by 5.93 rate of hydrogen. So, to have a convenient answer, 11.11, hydrogen oxygen ratio becomes 1:8. Divide by 5.93, hydrogen ratio oxygen is 1:16. So this ratio is 1:8, this is 1:16, and these two are in a simple whole number ratio of 1:2. These are in a simple small whole number ratio, and therefore illustrate the law of multiple proportions. We can write another numerical and leave it for you and leave it for you. If need be, I will attempt it in another lecture. In a compound of carbon and oxygen, the former is 27.27%. In another compound of these elements, in another compound of the elements, the latter means oxygen 57.14%, which law of chemical combination is observed. Should I leave it up to your wisdom? Same way, carbon is this, subtract from 100, that will be oxygen. Oxygen is this, in the second, subtract from 100 and it will be carbon. So, from these two values of carbon and oxygen, we shall mathematically prove that it illustrates the law of multiple. We move on to another law of reciprocal. Proportion. It is about combination between three elements, two at a time. We have a set of three elements, say A, B and C. A and B form a compound AB. B and C combine and form a compound BC. A and C combine and form AC. We shall first of all discuss an illustration, then try to define the law. We have, say, A, this is B, and this is C. Symbolically, there is a compound AB. Symbolically, compound AC. Symbolically, it is BC. Number one, molecular formulae could be different. Could be AB to A to B, AC to A to C, B to C, or BC to. That is very general thing. Out of these three, you may keep A at the top, write B and C, B at the top, write A and C at the top and write A and B. That creates no difference. Because three compounds, and we are to discuss weights or the ratio between weights of A and B in this, A and C in this, B and C in this. This law says we shall be having some experimental data. Some weight of B combines with a given weight of A. Some weight of C will have combined with some weight of A. The law says weights of B and C, B vakra, C vakra, which combine with the same weight of A. In this AB, there will be some weight of A, some weight of B. We shall calculate the weight of B which combines with some weight of A, say 1 gram. In this compound, we shall calculate weight of C which combines with same weight of A, maybe 1 gram. We will have values of weights of B and C which combine with A to form AB and AC respectively. We shall note the ratio between weights of B and C which combine with the same weight, or to be more specific, 1 gram of A. We shall, in this compound B and C, find the ratio between the weights of B and C which have, when these have combined directly to form BC. Ratio between weights of B and C which combined with, say, 1 gram of A on one hand, ratio between weights of B and C which combine directly on the other hand. These two ratios must be same, or this ratio must be a simple whole number ratio of the first ratio. Weight of B and C combine with 1 gram of A. These weights will be written directly and, say, try to find some relation or find some ratio. It is followed by weights of B and C which combine directly. Here also we shall find the ratio between weights of B and C. This ratio and this ratio must be either same or simple whole number multiple of it. This is the law of reciprocal proportion. We may have a direct example. We may have a example directly. Then we shall write the definition of law of reciprocal proportions. It is slightly difficult as compared to law of conservation of mass, law of definite proportions, law of multiple proportions. Now this is about 3 elements. This is about 3 elements. 2 of these combine at a time, A and B, A and C, B and C. The A, B and C do not combine together. Let us have a direct example. Say it is a carbon, it is a sulfur, it is oxygen. We could write carbon here, sulfur here, oxygen here, makes no difference. We could have written sulfur here, oxygen here, or sulfur